So in probability, we'll be looking at probability theory. And then we are going to learn one theorem called Bayes Theorem. You need to understand probability theory first before you can understand Bayes Theorem. Otherwise, you'll be very, very confused. Okay, so let's begin with probability theory. Remember in the lecture, I demonstrated in front of you. If I'm an archer, I'm holding a bow and arrow, and I shoot the bullseye from very, very near. The probability of hitting the bullseye is very, very high, almost 100%. But the further I stand away from the bullseye, the probability of hitting the bullseye is getting less and less. Okay. Okay. Another probability is like this. Imagine this target, the bullseye is yellow color. This first target B1 has no bullseye. So what is the probability if I shoot my arrow at this kind of a target? Will I have any possibility of hitting the bullseye? Will I have any probability of hitting the bullseye if I refer to the first target? There are how many targets here? There are 1, 2, 3, 4. 4 targets, right? So if I shoot the arrow to the first target, will there be any bullseye for me to hit? Bullseye is the yellow center. Bullseye. Will there any possibility for the first target? I hit any bullseye in the first target? What is the probability?
No, sir.
No, zero probability. Because there's no bullseye here, right? But look at the second one. If I shoot my arrow, boom, didn't hit. But still, there's a possibility I hit the bullseye if I'm a very sharp shooter, right or not? But the chance of hitting is quite difficult because you see the bullseye is very, very small. Now let's look at the third target. What is the possibility of hitting the bullseye? Is it better than the second target? Than B2? The answer is yes, right? Because the bullseye is bigger, right? So when I shoot, I hit here, also hit the bullseye. I hit here, bullseye. I hit here, also bullseye. Just now, if I hit here, now check bullseye. I must hit exactly here only. Considered bullseye, right? Now let's look at the target number before. What is the chance of me hitting the bullseye? Almost 100%, right? I hit anywhere on the target, it's already the bullseye because the bullseye is so big, right? So the bullseye is the probability of hitting the bullseye is 100%. The probability of hitting the bullseye on target B1 is 0 because there's no bullseye. The probability of hitting bullseye in target B3 is better than B2. So the probability is counting the chances. What is your chance? Yeah. And there are many problems in life, that can be described mathematically using probability theory for anything that involves chances. Yeah. Now, not just gambling. Gambling is a game of chance. But let's say, what is the chance of getting into accident? If you are working for insurance company, you are working as an actuarial scientist. Now, there's a field of mathematics called actuarial scientists. These people, their job is to determine probability, right? So these people, they know how to use what data to determine the probability so that they know how much premium to charge the customer. So that the insurance company will stand to gain more than losing. So they need to know the probability. Yeah. So that's why the probability may be useful. Yeah. It can be applied. How about in computer science? Of course, in data analytics, for example, in determining the probability of failure, probability of being attacked in cybersecurity, probability of the data being encrypted data being decrypted. So all these involve probability, right? So like in setting up a password for a computer system. Now, all passwords can eventually be cracked by guessing. Eventually, if you're very, very lucky, eventually there will be you'll be able to crack any password. The thing is that, do you have the time to spend your whole life or more than 2 or 3 lives to test every combination? So they are increasing the probability for you not to crack the password. So that's what they do. Yeah, that's where the probability comes in. Talking about the application of probability. Now, all of you have a ATM card, right? So ATM card, you're using PIN number. You're not using password. You're using PIN number. PIN, actually, I shouldn't call it PIN number. I should just call it PIN because PIN itself is already, the last letter in PIN is number. It stands for personal identification number. So the PIN for any ATM is only 6 digit. 1, 2, 3, 4, 5, 6, or maybe any number. Only you yourself know, right? It is not a password. Password is something like for your email, for accessing your email inbox. You need password. Password is a combination of numbers, alphabet, and symbols. Now, in your opinion, which one is easier to be cracked? PIN or password? Provided that the password must be more than six places lah, you know. If the password is just one place and it's easy to crack. Let's say PIN number is 6 digit. Password is also minimal 6 alphanumeric and symbol. Which one is easier to be cracked? PIN or password?
PIN.
PIN, yeah. Let's say lah, I just give one example. Let's say lah, you know, a very naughty friend, has stolen your ATM card tonight. Has stolen your ATM card tonight. So while you are sleeping, that naughty friend goes to the ATM machine. He has your ATM card, right? So he insert the ATM card. So he doesn't know your 6 PIN number, right? So what does he need to do? He type 0000000. Cannot? Okay, type again. 0000001. Cannot? 0000002. Cannot? 0000003. He can keep on typing until he gets until 99999. One of the number will definitely be a PIN number. Correct or not? Correct or not? That is just simply guessing the number systematically, isn't it? You put in your ATM card and then he type the 6 PIN number starting from 0000 and keeps repeating until 99999. One of them sure kena. One of them surely will be correct, right or not? But will that happen or not in reality? Let's say that naughty friend has your ATM card and he has the whole night in front of ATM machine while you're sleeping to do that. But the bank is also smart, right? So how do they prevent that? Definitely PIN number is easier to be cracked than password. But since PIN number is easy to be cracked, so how does the bank make sure that how do they prevent that? Even though it's easy to be cracked. So what do they do? Number one, you need to have the ATM card. No ATM card, you have the PIN number also useless, right? But let's say you have the ATM card and you have the whole night to guess the PIN number. Why? How does the bank make it difficult? Make it difficult or close to no, that's very less likely for you to break the code. How do they do it?
The number of PIN.
Yeah, you have 6 PIN number, right? You can type 0000000. Then you try again 0000001, 0000002. You keep trying, you know. You do for how many thousand times? you do for 999,000 times. 999,999 times. Surely one of the number will kena, right? Correct or not? But it's very tiring to do that. Now, how many times you can insert PIN number? Incorrect PIN number. How many times?
3 times.
3 times. After 3 times, what will happen?
Block.
It will swallow your ATM card and will block, and you won't be able to type your PIN number. So you only have 3 times, right? So you don't have the. So don't worry, like, if your naughty friend stole your card and then he tries to guess your PIN number, he has only 3 chances. After the 4th one, the ATM will swallow the card. That's how the bank overcome the shortcoming of PIN number lah. But they still use PIN number instead of password because it's easier to remember PIN number than password. And also it makes it easier for the computer to process. If you use password, is more complex calculation, right or not? Because the pin is actually stored on your card, and also there's another copy on the database to cross check. The pin number is actually stored on your card, in the memory of the card. All right, so okay, that's one example, how probability is used in IT or computer science. When we in cybersecurity, we can always invent mechanism or different techniques and make the process harder to be cracked by increasing the by reducing the probability of it being cracked. So in probability theory, okay, let's come back to the maths. In probability theory, probability is defined by dividing the number of desired outcome over the total trial. The bottom is total trial. The maximum number of times you try. S is the maximum sum of times, maximum sum of times you try. And E is the one that the expected number of times. The expected one that gives you the correct one. Yeah, expected over the sum. So PE is the fraction of possible times in which E is true. Okay, let's visualize this theory. Venn diagram. So suppose that we have Venn diagram. It's red in color. So anything inside this Venn diagram, the whole area, the whole area of the Venn diagram is 1.0. Yeah. And then you see the circle, the yellow circle here. The yellow circle here is the space within the Venn diagram where it is possible for it to be true. Where it is possible for it to be true. So the area of the circle divided by the total area of the rectangle gives you the probability. So what is probability? Probability is you take the subset divided by the universe set. Okay? If this is if we illustrate probability as Venn diagram. Any question on this? Concept, This is concept only, Okay, I move on, Okay, the answers are already there. But the question is, do you know how you get the answer? All right. What is the probability of these events when we randomly select a permutation of 1, 2, 3? Okay. So what is the probability of these events? So events here refer to A, event where 1 precedes 3. B, event that 3 precedes 1. And then C, event that 3 precedes 1 and 3 precedes 2. So what does this mean? Please try to read and understand on your own first before I explain, because this requires some analytical thinking to understand what it means. No insult if some of you actually, the moment you read it, you already understand, no insult, because I think some of your friends probably need some time to read it. If you already can understand immediately, good. Try first. See whether you understand or not, how the answer is acquired. Precede means comes before. Precede means comes before. That means if we take the number, we take the number and the number only 1, 2, 3. 1 precedes 3 is like 1, 1, 2, 3 is 1 precedes 3. 1, 3, 2 also 1 precedes 3. But 3, 2, 1, no, because 3, 2, 1 means 3 happened first, then only 1. So in this case, 1 does not precede 3. Okay, boys and girls, I hope you're trying before I explain. Otherwise, you are just listening without understanding. Okay, I explain. You still remember or not permutation? So we have a set of three numbers, 1, 2, 3. Now, permutation means we take 1, 2, 3, we arrange it differently. Permutation means we arrange the numbers differently. So how many possible permutations here? You see here? 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So any more? Any more possibility? No more already. How many permutation here? 1, 2, 3, 4, 5, 6. So we can take 1, 2, 3 and arrange them 6 different ways. That's what permutation is. If you don't understand permutation just now, by the time you reach here, you'll be confused. If you don't really understand permutation, I hope everybody understands. So how many permutation? Yes, 6 permutation, meaning that I take 1, 2, 3, I combine it in different way. Maximum, I have 6 different combinations, 6 different arrangement. Sorry, not combination, 6 different arrangement. That is permutation. Permutation is about arrangement. Now, the question is, what is the probability that 1 precedes 3? That means 1 happened before 3. Now, let's look at A, 1 precedes 3. So we analyze this one. 1 happened before 3. Correct? Yes? Yes. 1, 3, 2. 1 precedes 3 or not? Yes. 2, 1, 3. 1 precedes 3? Yes, because 1 comes before 3, right? How about 2, 3, 1? Yes or no? Does 1 precede 3 in 2, 3, 1? Precede means that comes before. No, because 3 appear first, then only 1, right? So correct. Sabrina, you're correct. 2, 3, 1. The 1 does not precede 3. All right? So no for 2, 3, 1. I just color code first. And then 3, 1, 2. Also no, right? Because you see 1 appear after 3, right? It should be before. Precedes mean before. So also no. How about 3, 2, 1? Of course no, because 3 appear first, right or not? So in this permutation, only 3 times. Only 3 times where 1 comes before 3, which are 1, 2, 3, 1, 3, 2, 2, 1, 3. So the total number of permutation, the total number of all possible permutation is 6, right? But out of these 6, only 3 satisfy the event where 1 precedes 3. So the probability is we take how many of this correct, the E part, which is 3, divided by the total one, the sum of all, 6, 3 divided by 6, 1 over 2. So the probability where 1 precedes 3 is 1 over 2. All right, so I'm not going to discuss B because the idea is almost the same, but I want to discuss C. Okay, I want to discuss C. So I will go back to this permutation again because again it's based on the same problem. We have 3 digits, 1, 2, 3. We arrange them differently. What are the total number of arrangements? What are the total number of permutations? What are the total number of orders? The total number of orders, permutation, or arrangements are 6, which are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 2, 3, 2, 1. No more already. No more already. Maximum already. Yeah. This is given by NPN. I take 3. I want to choose 3 out of 3. Remember the permutation formula or not? I'm taking 3. I'm choosing 3 out of total 3. So how many possible combination? If you remember, 3 asterisk divide by 3 minus 3. This is the formula because the formula is n asterisk divided by n asterisk divided by n minus k asterisk. That's the formula for permutation. Yeah, you check back the formula. Please memorize it. In the final exam, I will put the formula there, but if you have to refer to the formula all the time, that means you're not skillful enough. You didn't have enough practice. So it becomes 3 factorial divided by 0 factorial. So boys and girls, what is the answer for 0 factorial? Zero factorial. What is the answer for 0 factorial?
1.
Correct. 1. Good. 0 factorial is 1. 3 factorial divided by 1. So we don't bother already about the bottom lah. We just need to solve 3 factorial, which is 3 times 2 times 1. Total number of possible arrangement, 6. You see? 1, 2, 3, 4, 5, and 6. Yeah. So I'm just showing you how we can apply the permutation formula. Okay, so this one I just put aside because it's an additional footnote, not part of the slide. I just want to explain how we actually determine the number of possible permutation from the formula. If you learn well from the previous chapter, you should be able to get this. Okay, so we want to look at the event where 3 precedes 1 and 3 precedes 2. Now, 3 precedes 1 and 2? Yes, no? No. No, so I put red. Now, does 3 precede 1? Yes, but 3 does not precede 2. Sorry, does 3 precede 1? No, 3 does not precede 1, but 3 precedes 2 only. So it still cannot fulfill the formula, fulfill the criteria, because it says and. 3 precedes 1 and 3 precedes 2. So it only precedes 2, but it doesn't precede 1. So cannot, reject. 2, 1, 3. Does 3 precede 1 and 3 precedes 2? No. Yeah, because you see, 3 is after both of them. So reject. Now, does 3 precede 2 or not? No. 3 only precede 1. So again, reject. But let's look at this. Does 3 precede 1 and 2? Yes, because it appears before 1 and 2, right? So we accept this. Good, we accept. How about this one? 3 to 1? Again, yes, it appears before 2 and appears before 1. So the only time when this criteria is satisfied is 2 times only. The total number of permutation is 6. But the number that satisfied this event is only 2. So that's why we take 2 divided by 6. That gives us probability of 0.333 or 1/3. All right. So I hope everybody got it. Okay, there are many, many slides. If I explain the example one by one, we'll never finish. So the rest, I show one example. The rest, I hope that you try to figure out on your own. You can ask friends or you can ask in Facebook group, But you must try first. Don't just ask friends and then don't be a parrot. The parrot is a bird, right? Whatever people say, it will just repeat back. But it doesn't know. I don't think it knows what it says, right? Maybe it does, but don't be a parrot, yeah? Make sure you understand. So we can use another type of probability that is called conditional. So the keyword here is conditional. So what is so great about conditional probability? Conditional probability means there are 2 happenings. Happening number 1 and happening number 2. Happening number 1 must happen, then only happening 2 will happen. That is called conditional probability. Now, just now, all the examples we see is just probability. Whereby, for example, this one is not conditional probability. This one is not. The probability is whether I hit the bullseye or not. So there are no happening, right? Just one happening, just one event only. What? Whether I hit, I don't hit. One event only. What? But conditional probability means there are 2 different separate events. The question is, does the next event happen after the first event? Quite abstract. What is this lecture talking about? And do you know what I'm talking about? Let me think of one analogy. Analogy, let's say, If you hear the thunder, rain will follow. If you hear the thunder, rain will follow. Is this true or not? Oops. Is this true or not? If you hear the thunder, rain will follow. Is there a truth in this statement? Anybody? Is there a truth in this statement? How many?
Sometimes,
Sorry?
if you hear thunder, sometimes rain will follow.
Sometimes rain will follow, right? So that is a partial truth, correct or not? That is a partial truth. But it's not wrong also, isn't it? You cannot say zero. This statement is zero probability. You cannot say like that, right? But you cannot say it's 100% probability. So are we able to determine the probability? Like, okay, if you hear the thunder, rain will follow 50-50, 50%. Is there a way for us to compute? The answer is yes, but we must have the data lah. We must have the data. Yeah. So this is what we call conditional probability, because you see, first we must determine the probability of thunder. Then we must determine the probability of rain. Then only we determine that rain will happen if you hear the thunder. So you need probability of thunder, probability of rain, and finally to determine probability of raining if there is a thunder. That is why it's called conditional probability, because there is a condition, and the condition is, in this example, hear the thunder. So okay, just 1 minute. Please read the rest of the slide. I'll get back to you. Just give me 1 minute. So ask yourself, do you have an idea what is conditional probability versus the single probability? I hope you have the idea now, yeah? Okay, so if you hear the thunder, rain will follow. At least you remember this lah. Okay, let us dissect this. Suppose that event B is observed to follow event A. Thus, event B is dependent on event A. It'd be interesting or useful to know the probability of B depends on that A of happening. This is given by P, probability of B given A happens. Probability of B given A happens. Probability of rain given thunder happens. Probability of rain given thunder happens. Do you see that? Conditional probability. So how do we compute conditional probability? That's a formula. Okay, we don't have to figure out how this formula is derived. Yeah, not in the intention of this class. You just need to know that this is the formula: P, B, and A over PA. Now, we can actually make sense of this. Let us look at the thunder and the rain and relate that to the formula. Look at this analogy I give you and relate to the formula of this formula. See whether you can make sense of it or not. How you determine probability that probability of rain happening if there's a thunder. So if you're a scientist, right? You are the weather scientist. Let's say you're a meteorologist. Meteorologist is the weather scientist. How do you determine the probability? So what kind of data you collect? So you observe the weather, right? So you observe the weather when there is a thunder. Every time there's a thunder, you count. Every time there's a thunder, you count how many times. And then you also count every time there is a thunder and there must be rain. If thunder, no rain, you don't count. Thunder and rain only you count. Then you divide thunder and rain, divide thunder. Thunder and rain, divide thunder. You will get the probability of it rains after a thunder, which is definitely not 100% because not always. But is it 70%, 80%? Or is it 5%, 1%? See? So, application. How is this useful? And again, for example, you determine the probability of air crash happening if you fly in an airplane. Given that probability of you flying in an airplane and probability of somebody who rides an airplane and it crash. To determine that is the probability. Yeah, that's how you determine probability. An example application. And then another possibility, all right, is what is the probability that if you see someone having sore throat, that person has COVID-19? Is it true all the time? 100%? No, because sometimes people are just having normal sore throat, nothing to do with COVID-19. But is it 0%? Also no, right? Because people with COVID-19, they have sore throat. But the question is, do we really need to be scared when we see somebody with sore throat because we fear that he or she may have COVID-19? Let's say the probability of that is 99.99%. Yes, please be scared. But let's say the probability of somebody with sore throat and having COVID-19 is only 10%. Out of 10 people with sore throat, only 10 of them have COVID-19. So 10%. So the probability is quite low, right? I mean, there's still risk because out of 10, you have one. But let's say the probability is 1 over 1,000. Probably you can neglect because it's very small, right? What is the chance you meet 1,000 people with sore throat? That person will be having COVID-19. You must be very, very unlucky for that to occur, right? These are some of the examples, popular examples. Please study this example very, very well for your test and anything else. Okay, so please study it very, very well. Okay, this is another example, and I show how we actually calculate it. Yeah, of course, it's not something that you just read through one time and you understand. Try to work it out and recall the formula and how they're being used. All right. I want to move to the third part. We are done with the simple probability. We are done with conditional probability just now. Now we are looking at Bayes Theorem. So if you don't understand conditional probability, you have problem understanding Bayes Theorem. You must understand you must understand conditional probability first. Okay, that's the prerequisite. That's why we arrange it this way. So Bayes' theorem says, for a random event, how likely is it going to happen? Okay, again, it's conditional theory. It's conditional probability, but this is more sophisticated. See how we use it. Bayes' theorem describes that the probability of a random event is based on prior knowledge of conditions. Okay, so this is where prediction happen. In the mathematics of prediction, we need two events: the earlier event and the event that happens after. So what is the correlation? If the correlation is very high, that means 100%. Every time event A happens, event B sure will follow. But if the probability is low, the correlation is low, event A happen, event B may not happen, 50-50, or maybe 1 in 10 possibility. So Bayes theorem provides us with a mathematical tool to revise our belief about the relationship of two events. Yeah. So if 100%, that means the previous event is an evidence. If it's not 100%, that means the previous event may not be an accident, it may be just coincidence. Coincidence versus evidence. Coincidence means the probability of Bayes theorem is very, very low. It happens together, but it's just coincident. Evidence means almost 100%. So it's a clear cut. Number 4, suppose that A and B are events from a sample space set S such that PA is not 0, PB is not 0. That means both has some probabilities. Then the relationship between them is given by the following formula. Okay, how do we use this formula? You see here, B given that A happened, A given B happened. Okay, how to make sense of this? Let me put it this way. If there is a thunder, rain will follow. If there is a thunder, rain will follow. Now, the other one is, if there is a rain, there will be thunder. If there is rain, there will be thunder. The first one, if there is a thunder, there will be rain afterwards. The second one is, if there is rain, there is a thunder. You see, these two different events, these two different conditional probability can be related by Bayes theorem. Bayes theorem can relate P, A given B to P, B happening given A. So this is the use of that formula. But of course, in order to derive PBA to PAB, we need other data like PB and PA, probability of B happening, probability of A happening, independent of other factors. If you know the conditional probability, you can use the Bayes rule to find out the reverse probabilities. The reverse, see, PBA versus PAB. Are you following me? I'm not going to explain this. I think you can read this. One example application of using Bayes theorem in Google search. Okay, this again is explaining to you the Bayes theorem part by part, the components. What is this? What is this? What is this? What is this? Yeah. The other equation, there are two equations. You either use this one or you can use the other type. The other type is harder to memorize, but the first one, okay, it's not so bad, no? You still can memorize. And don't worry, in final exam, I will share this. If I ask this, I will share this formula. Yeah, so that you won't crack your head too much memorizing too many more formula. I want you to understand rather than memorizing formula. But of course, very, very simple one you have to memorize. If not, come on, I cannot be giving all the formulas, right? Okay, this is another example. Like I say, understanding mathematics is best done by doing them and understanding the examples. All right, so this is another example. If there's smoke, there's fire. What is the probability? If there is fire, there must be smoke. Let me ask you. If there is smoke, there is fire, right? But what is the probability of if there is a fire, there will be smoke? Not all fire comes with smoke. Chemical fire that has no smoke sometimes. Yeah, some chemical fire has no smoke. Smoke is water actually, H2O, evaporating with other dust. Okay, another example, which I don't intend to go bit by bit. This will take at least 10-15 minutes. Okay, this is another formula. Rule of subtraction. Yeah. PA given B, 1 minus P inverse A given B. So if in case you see A inverse, right? Then the relation with PAB is given by this 1 minus. May be useful for some of the formula. When you use the formula Bayes theorem, it is good to know how you can do the algebra. Yeah. So there is a filter called Bayes span filter. Okay. It is used for determining possibility that an email is a spam email. They use Bayes theorem for that. So they identify a few commonly used keywords in spam email, and then they use that historical sample to compute the other email for being spam or not. So they use this formula. Yeah. So the formula for Bayes spam filter is simplified as follows. You see, it's the same formula. I'm just changing AB to SW. Yeah, I'm just changing AB to SW. It's actually the same thing. You see? Yeah. But of course, this one is more complex because it has S inverse and S inverse. Yeah. W given S inverse and S inverse. S inverse means the opposite. Let's say like if I say A is referring to it is raining. A inverse means it means it is not raining. Okay, another example of spam filter. So I give two examples of spam filter for the word free, and then for the word Rolex. Yeah. So all these, please read them for your understanding. Yeah. Please read them for your understanding. And they are also the Bayesian spam filter can be used with single words or multiple words. When you use it with multiple words, then the accuracy of a spam detection is higher. But of course, the formula becomes more complex because you have more than one words. You have 5 words, right? Then you'll be E1, E2, E3, E4, E5. Yeah. So there'll be more elements. So the computation becomes heavier lah. But the formula is the same. Whether if you're using 2 words, E1, E2. If you're using 3 words, E1, E2, E3. If you're using 5 words, E1 and E2 and E3 and E4 and E4, E5. So the formula is the same. Yeah, E1, E2, E3, E4, E5, E1, E2, E3, E4, E5. E1, E2, E3, E4, E5. Here it's up to E2 only because yeah, we are only using two words for the spam detection. All right. So it's an example. All right. So here comes the summary. Basic probability or discrete probability is very simple. Event versus the sum of the whole sample. Conditional probability is when one event happening followed by the other. Yeah. Discrete probability is just only one event, but conditional probability has 2 events whereby one event follow after another. Bayes theorem is a more complex derivation of conditional probability. You see, PFE. How do you get PFE from PEF? But of course, you have to find out other components like what is PF, PEF, sorry, PF, PEF, PEF inverse. Sorry, not inverse, not. This bar means not F, PE given not F. Sorry, I keep mentioning inverse. The word is not inverse. The word is not, NOT. Yeah, not inverse. Inverse is -1. Superscript -1. Here is just a bar. Bar means not, NOT, the opposite. So that's it.